Why did he say 1 moment? Oh, okay. I just want to start my timer. Okay. Now that the problems have been settled. So first of all, I want to start with a heartfelt thank you to Michael. I think that Michael changed the course of my life, really, and it's a huge thing to feel. It was maybe by chance, I don't know, but when I came to him and I started working on my master's, he gave me a problem which really sort of paved the way to the future. And there were a few things about the fact that he gave me this problem. First of all, it was a problem that he didn't know if it could be solved. And in fact, people thought that it could not be solved. But still, this is part of how Michael thought about things. He believed. And he gave me that question with a full sort of confidence that it can be done. So of course, there's the operational thing by which he changed my life by giving me this problem. But that was not the only thing. It was also the excitement and the love. And Avi touched about it, about how Michael would love to talk about things and tell you new things. But it wasn't, okay, yeah, you know, there's this new theorem. It came with a passion. And that passion was also, I feel, transferred to me through the years that I worked with Michael on this problem, and really made a huge, meaningful difference to me. I have to agree to that, because I agree that that passion, maybe it's just... Oh, okay. So my father is Michael's advisor. So it's a generational thing. But Michael was an amazing student, because he really, the passion and the love were always there. And I want to say one thing, because I'm looking for ways that I am unique. And yesterday my bubble was blown on the fact that I'm not the first student, but I think I'm the person in this room, not excluding Nava, who knows Michael the longest. Because I met Michael when I was a little child, and Nava met him only later. You know, I didn't sleep the whole night trying to figure out how I'm unique. So there it is. You agree? Okay, good. Now we can get to the talk. Okay, so I want to talk, really, it's about this work that Michael and I had worked on together. But before that, really the work that sort of led to these things, and it relates to information theoretical multi-party computations. There'll be a little bit of technical stuff at the end, but I really want to tell sort of the story and how these things came about and how they can be used in what's happening today in this world. So, and I knew that this was not a cryptography audience, so there's really maybe more fundamental cryptographic things that crypto people would know, but I think that they're so beautiful that came from Michael's work that I want to mention. So the question of multi-party computations was introduced by Yao in the beginning of the 80s, and it basically asked a really, really simple question. There are 2 millionaires, and they want to know who's richer. But of course, there's a trivial way to solve this question. Gates says, I have 100 million, and Bezos says, I have 101 million, and they know who's richer. But they don't want to expose this information. They only want one bit out. Who is richer? Without their individual fortunes being known. Of course, today nobody would talk about millionaires, we'd have billionaires, and we don't only want to look at the question of 2, there could be more, for example, 3. And what we want to do is to compute a function f of their inputs, and while preserving the privacy of their inputs. So if we generalize it any further, we have n parties, they hold these inputs, and we want to compute any function f, not just the max. any function. And we want to do this also in a setting where some fraction of the parties can be malicious and would want to obstruct the computation. Maybe they'd want to do it by learning more about the inputs, maybe by causing people not to get the correct output and so on. There's a lot of things where we say that parties can be faulty. I'm not specifying here how. We want to protect them against faulty behavior. So yeah, when he introduced the question, he immediately gave an answer. But he did this in the computational setting. And what does the computational setting mean? It means that we're making some assumption about the computing capabilities of the parties, one, but also on the computing capabilities of the attacker. So we say that the attacker and the parties are bounded, that they cannot compute indefinitely or with unlimited computing power. And basically what it means is that they can't break the underlying cryptography. All our cryptography is based on some assumptions. Old assumptions would be the complexity of computing discrete log, factoring numbers. Today with new systems, we have assumptions about some computational assumptions about lattices. But in all these cryptographic systems, there is an underlying computational assumption. And Yao's solution is in that model. So are we done? Is the fact that we have a solution which works in the computational model, does it say, okay, we don't need to solve anything? But the question is, can we do better, maybe without an assumption, but also differently, not just because we can eliminate the computational assumption. And it's important to do so because we don't know really that these computational assumptions will hold forever, right? For example, if quantum computer comes along, that we know that discrete log and factoring will not hold up. We don't know about lattice assumptions, but this is where we are. So we definitely want to try and give solutions that do not rely on computational assumptions. And this was what came up with Michael, and in fact, we have Shafi and Avi here too, with a really groundbreaking result. And we also have Claude Crépeau here. We don't have his other two co-authors, but there were these two papers that came up. I always say it's amazing how these things happen at the same time. Problems open for a long, long time. This one was not, but then suddenly there are two solutions. And they came along and they said, what can we do? Can we do without computational assumptions? Can we try to solve this in the information theoretic setting? And something else that I love about this problem is that it came from pure theory, really from an interest in these fundamental questions without thinking about where it could lead to and so on. And I will talk later about the fact that it really came up, and now there are things that people are thinking of really deploying in practice. What was nice about these things, about the information theoretic, as I said, it was a curiosity on the intellectual side, but the truth is that these information theoretic solutions are also quantum secure. If the solutions that you have are based on discrete log or factoring, which Yao's of course were, those would break. But these solutions will withstand also a quantum computer. So they give you, in the lens of time, you also see that they have this very nice addition that they're safe about against quantum machines. And also, what is very interesting is that these solutions are extremely fast and the computation is low, unlike the computational solutions. So really, they came and they gave a huge advantage that now we see when we're optimizing things. And that's why I said that these are techniques that are very good in the test of time, because they really can get you efficient solutions, which is very nice. So we believe in these techniques. As I said at the beginning, they were theoretical, but already by the late 90s, we were thinking that we really can do a lot with these things. And there's a lot of places to actually use them in real applications. For example, for bidding, think about it. What are we doing? We're computing a function where we're preserving the privacy of the inputs. So it's a classical solution for a bidding system where you want to put your bid, the parties will compute the answer, nobody will know your bid, and the only thing that you will learn is the person who won the bidding. So perfect for that. Voting. Everybody enters somehow their vote, and all you get is the output. In recent times, most likely a very disappointing output, but you get the output of the vote. Okay, and for medical situations, you have 2 hospitals who have patients who have the same disease. They can't share the information, but they want to conduct the research. So you can do some computations that they can work in a multi-party computation setting and get the answers of the research. And also, this is a more recent thing. You can use these for techniques for cryptocurrency wallets. This is a little bit more of a threshold solution, but it's also under the general umbrella of multi-party computations. If you don't know what threshold is, it doesn't matter. But what it enables you is to take your secret key, which signs transactions for the blockchain, and somehow distribute it and then compute the signatures. And it provides a heightened security for the secret key. Okay. But in practice, not much has happened, definitely so far. Any person who writes a paper on multi-party computation quotes mentions some sugar beet sale that happened in Denmark. And that's about as far as it goes. We don't have many other uses of these things. But help is on the way. And why is help on the way? Because privacy legislation is becoming extremely popular all over the world. And basically what it's saying is you have to preserve the privacy of the inputs of the parties. And we're hoping that these things will really sort of give a push forward to these techniques, that research will start using it, that advertisers will use it, and I'll get into it. So MPC to the rescue. Yes, we can, we know how to do it, and we have all these great solutions. But I want to say that even if it does come about that these privacy legislations will say you need to use these techniques, they have to be deployed, because otherwise you can't achieve what you want, we still have a lot of challenges. And this is something that I'm very happy about, because it'll offer me employment for years to come. And because things need to be done at this point and improved. And what are the challenges? I said that we have a theorem, which BGW and CCD and Yao and so on gave us. We know how to compute any function. And a generic solution is given which solves the problem. However, these generic solutions are not fast enough. And what we've discovered is that if we build a dedicated solution to a specific problem, for example, we had a paper on how to do some genetic computations. When we did a back of the envelope calculation for the generic solution, it was something in the order of days. When we designed the dedicated solution, it was in the order of 2 seconds. So the question is, what do we do with the fact that generic solutions are not fast enough? We need to build dedicated solutions. But the issue is that these dedicated solutions need to be designed by experts. Really, only cryptographers at this time can build dedicated solutions which are efficient. And we have another issue, which is proliferation of models. I won't discuss about it. So we really have to find some way that we can make this more mainstream. But these challenges all exist of what do we do? So there's great opportunity ahead. Unfortunately, most of you are physicists, so I don't know if I'll attract you to our area. But if you're still in the stages of deciding what to work on, these areas are really amazing. So I want to give a few more examples of things that are becoming relevant now. For example, ads. Ads, maybe due to legislation, but also due to the dynamics of big players in the ad industry, we're utilizing up to now what is called third-party cookies. You go someplace, they know who you are, they know what you're looking at, they know where you clicked, where you went to, you're tracked completely. But there's going to be a deprecation of third-party cookies just because basically Apple led this and they said they don't want to be tracking anymore. And now companies are not going to be able to do this tracking. And the question is, how will they get the information which they so dearly need in order to make revenue and in return provide us with things that we want? I mean, Google, all of their services are free, but you get them because they're really making money off of ads. So how do we still compute things that interest advertisers? For example, how far did the campaign reach? How many people did it reach? And the beauty is that you can really give solutions to these things without exposing individual users. So you can deliver these solutions to advertisers if you want to. As I said before, again, medical computations can enable to do research that people want and is critical, life or death sometimes, and we can do solutions. Now, another thing which has come up with the proliferation of machine learning and so on, and that's federated learning. What is that setting? You have a big company, let's say JP Morgan, and they have millions of users on their cell phones doing all kinds of things. And they want to run some learning algorithms on their clients. But the clients don't want to share exactly what they're doing, but they are willing to participate in some computation that will deliver aggregated answers to JP Morgan. So federated learning is now a huge area that deploys multi-party computations and is in fact being used. Google has deployed it already. They have solutions that do these things, but these are all really multi-party computations in their essence, and they provide better privacy for users, but still utility for the companies. Okay. So I said, and this is something that I want to say sort of is a way that we're thinking of doing research going forward and has already been started. I said, we have the generic solutions, we have the dedicated solutions, and the difference between the runtime is huge. But maybe, and this people are starting to build, maybe we build little building blocks. Maybe for something, Byzantine agreement, which Michael has a paper on, secret sharing or set intersection. And we build these little building blocks and we optimize them somehow. And then we really enable people to design the protocols using these building blocks by giving them some glue of a programming language and so on. So this could be a step, maybe an intermediate step between the generic and the dedicated, and could increase the number of people that would actually be involved in the design of such protocols, because they would really need to have maybe a lower understanding of the cryptographic design and could build these things. So this is something that people have started working on and are thinking of, and it sort of gives some middle ground. Okay, so now I want to talk a little bit about the paper of Michael, Shafi, and Navi about the paper that showed us that we can do information theoretic MPC. And I want to say again, Avi was talking about this also, sort of the algebraic love and sort of the lens through which Michael sees things. And I do think that it's this mathematical basis and the algebra looking of it all. And you'll see when we get to the solutions that how it lies there so beautifully. And as I said, there was also the paper of Claude and David Schaum and Ivan Lamgard. Okay, so let's go back to our problem. What do we want? We have these n parties and they each have an input, and we want to compute a function of these inputs while preserving the privacy of the inputs. So I said that we will look at a case where there are faulty parties. The paper deals with a case where there are faulty parties, but I will not discuss it here now. I'm just going to show you the math, sort of the basics that it somehow was built on. So Shamir showed a notion of sharing a secret. And what did this secret sharing meant? It meant that there are n parties. You have a secret value, x, and you want to distribute it amongst people so that each individual person does not know the value, but together they can combine the value. Let's say, simplify the idea. I have the number 10. I give the number 12 to Dorit, and I give the number -2 to Shafi. Dorit on her own with the 12 doesn't know that my number is 10, and Shafi with the -2 has no information about my number 10. But when they get together and they add the numbers, they learn that my secret is 10. Okay? I gave an additive secret sharing here, but Shamir had a wonderful idea, and he did the secret sharing via a polynomial of degree t. T is the number of parties that you think might be faulty, but you have t plus 1 parties that can reconstruct the polynomial of degree t. And any subset of t plus 1 parties that get a point on this polynomial, you can give n points, as many as you want, they can reconstruct the secret. Okay? Is this clear? Are there any questions about this? Okay. So we have the secret sharing, and this is where we were. This paper is from 78, I think. Now I might be wrong about the year. And this is where we were. And now came the idea of BGW. First of all, Shamir's thing did not have fault tolerance. He just said you distribute a polynomial of degree t, and t plus 1 can reconstruct. But part of the beauty of the BGW paper is that they said you can have n parties, t might be faulty, and you'll set n to 3t plus 1. And what does it mean that t are faulty? That maybe when you come to reconstruct the secret, t people will give you garbage. They will not give you points on the polynomial. But since we have error correcting, we will use that in order to deliver the result. So now suddenly our protocol has some fault tolerance. And we can withstand a third of the parties being faulty. Okay? And this, by the way, is tight because we have a lower bound for the error correcting. Okay, so then we had secret sharing, but that was it. We really wanted to be able to compute a function. This was our goal, right? So what the BGW and CCD framework said was, let's look at the circuit that computes the function. It basically consists of additions and multiplications. So let's give a way to add and to multiply. We'll start with the secret sharing. This is how we'll introduce the inputs into the circuit. And we will design our gates, the addition and the multiplication, so that at the end of the addition, we will still have here some secret sharing representation of now the sum of the two inputs and of the multiplication of the two inputs. Okay? Okay. And we shared. And we keep the invariant. I said everything. Okay. I want to add something about Shamir's secret sharing, which I did not say up to now, which is very important. The Shamir secret sharing, it was with a polynomial of degree t that we needed because we wanted t plus 1 parties to reconstruct the secret. But one other very, very important property of the polynomial was that it was a random polynomial. Okay? This was critical in order to preserve the privacy of the input, which was computed, I forgot to say, the secret was put in the 0 evaluation point of the polynomial. So it was a random polynomial whose constant term was the secret, and it was of degree t. And this was very important to provide the secrecy of the input. Okay, so now let's look at what they said to do for addition. We have the original secret sharing. This was one secret with the value x at the 0 point. And this is a second secret sharing of another secret, whose value is this, y, at the 0 point. Okay? Now, we have these two polynomials, and you can see very easily that f of 1 plus f of 2 at 0 is exactly what we want, is x plus y. We get immediately the value at the constant term. And now, what do people need to do? The parties have, each party has their share at their point. Let's say at this party, S3 has this point and this point, right? All they need to do is to add these points in order to have a point on the polynomial of the addition. Okay? And very nicely for us, it remains a polynomial of degree t, and it is still a random polynomial. Okay? So addition is beautiful. It's easy, and it's non-interactive because every party can do the computation locally, which is beautiful. So we get the addition really almost for free. Okay. But now, what happens when we want to multiply? Okay? Unfortunately, things are not so nice. Or maybe fortunately, because if everything was easy, maybe it wouldn't be as nice. But here is where sort of this algebraic understanding in depth I feel that this paper comes into play. And really one of a beautiful, Avi, you said gems? Gems? A gem. So what happened to us? We really are in deep, deep trouble, okay? We moved to a polynomial of degree 2t. Now we can't even do error correction, right? Because we don't have enough points because the polynomial degree is too high. But oh my God, it's not random, okay? It's now a polynomial of degree 2t. You know, it's not even a prime polynomial, right? We know that it's a composite, definitely not random, okay? So this was an amazing disaster, okay? So, but it did have one very nice property. The constant term was what we wanted, okay? The polynomial at the product was x times y. Okay, hope. Okay, so we need to do two things. We need to reduce the degree of the polynomial, and we need to randomize it, okay? And the BHW gave a beautiful solution to this, which was later slightly simplified, and I will give the simplified solution. So what do we have? These are the coefficients of the product polynomial, We don't know what they are, but they exist. A0 up to A2T. Okay. We calculated the share of each person of player 1 at 0.1, player 2 at 0.2, and player, I'm just doing the math, so I'm doing just 2t plus 1. We have 3t plus 1 points. Let's ignore it. At 2t plus 1 points, okay? And this gives us the evaluation points of the parties, what they have locally. Each one, because they multiplied, they have these things. So let's call this matrix A. And now let's look at this thing multiplied by the inverse of A, and we put this thing here, okay? What are we interested in? We're really interested in A0. We said that A0 was X times Y, right? We have what we need here. So now let's just look at what A0 is. H0 is the sigma of lambda I, the Lagrangian coefficients, times these alpha i's, alpha I. Okay? Now, the BGW paper showed us that we can do addition. I didn't tell you, but it also showed us how trivially to do a multiplication by a known constant. Okay? So basically, it gave us completely that we can do any linear combination for free. So we get it here. And now A0, we get automatically this value that we can compute. And now, how do we reduce the thing? So now we have, oops, okay. We have that every party can share their value with a random polynomial and we reduce the degree immediately because this is a linear combination of polynomials of degree t. And this is how it's done. Okay, I want to mention another gem that exists in this paper. I had showed you things that were in a single variate polynomial. But there's also a solution in this paper that does a bivariate polynomial. The disadvantage of the single variate polynomial is that it was had a probability of error. It doesn't matter where it comes in the correctness. But this thing enabled to eliminate this error, which I won't say how, but it basically gave you the idea of local consistency checks. And this really is an idea which appears in the PCP theorems. So really, this is an origin of this idea that by checking small things locally, you can really reach a global correctness. So I see this sort of as in a seed of something that existed, that was really used in a very powerful later. And then there's this generalization of whether we can go below 3t plus 1. And I won't get into it because I'm out of time. And what? It's nice. It is nice. Okay, I will do it. I'll do it very quickly. So this is the problem that Michael gave me when I started my master's. And he said, listen, can we go below the threshold of a third? Of course, we have to change the model. We have to introduce a broadcast channel because there's some lower bounds of Byzantine agreement. But can we do it? We can't use digital signatures because it's supposed to be information theoretic. And we can't use error correction also. So we're really, really stuck. These would have been two ways of maybe noticing that values that parties give are wrong, but you can't do signatures and we can't do error correction. So what do we do? So just a digital signature in the computational setting thing, we did want to do something like digital signatures. So how do digital signatures work? There is a secret key and a public key. They're a pair. The party knows the secret key, the public key, as its name implies, everybody knows. You get a message into the signing algorithm and you give a signature. And then somebody wants to verify the signature, takes the signature, the message into the verification protocol and outputs an accept or reject. All our solutions for digital signatures are based on some computational assumptions. So it has the property that there is one signer and everybody can verify. Everybody who knows the public key can verify. So if we had digital signatures, look how easily we can go below the lower bound of 3t plus 1. The dealer would sign every value that it gave a party. And now, when you want to reconstruct, you take only points that whose signature satisfies the verification. And now you know that they'll all be points on the polynomial. You don't need error correction anymore. So you can go below the bound of the 3t plus 1. So it's clear that digital signatures really help, but we don't have them. So the question is, could we do something not as powerful as digital signatures because we don't have computational assumptions, but can we do something at least as good? And the idea was that maybe you have a signer and he gives something to some person, sort of an intermediary. And maybe it can be verified only by a single party, not by everyone. But one individual can check if the value is correct or not. So how is this done? This was really done by something which is the following. The signer will give the message and some C value to the intermediary. And it'll choose, how is this C calculated? It shows two random values, A and B. So these A and B give the verifier no information about this message. And C is computed as AM plus B, okay? And now, when the intermediary gives MC to the verifier, the verifier checks this equation. If C equals AM plus B, and if it does, then it assumes that this value originated with the signer, okay? We don't get the full-blown idea that everybody can verify, but you can do a local verification. And this turned out, this reduced sort of information theoretic signature enabled to deliver the full solution of achieving MPC with 2t plus 1. Okay, so the road ahead on this areas are I think it's just an exciting road with a lot of twists and turns and a lot of interesting things and a lot of great work that can be done. And I want to say thank you to all of you, but mostly to you, Michael. You really have been a guiding light in my life on this front, and thank you very much.
Questions. Maybe the word you can tell us in this last picture with the three, who are they in the protocol?
Who?
Who are they in the end parties in the protocol?
The intermediate in the signature thing? Sure. Let's see if this, okay. So you had in the secret sharing, but you can just look at Shamil, okay? You had the dealer who had the original secret. He gave a share to each one of the end parties. And then at the end, when you want to reconstruct, everybody looks at all the shares. If they were digitally signed, each person locally could throw out the bad shares, okay? So in the information theoretic setting, the dealer will give this verification to every one of the people who's going to reconstruct for each one of the people who got a share, for each one of the parties that had a share. So now, when Dorit comes to reconstruct and this group sends her the secrets, she throws out the bad ones and interpolates the polynomial. When Charlie's interpolating, he gets from that with things with these information theoretic signatures that relate to him. It's an n-squared relationship.
Dealer may not be around.
The dealer's gone.
How is he giving it at a later time?
He gave it in when he shared it. When he shared the secret, he gave you a share and do it away to verify it. And your share can be verified by Charlie, okay? It's not sufficient to deliver the result. There's one component which I didn't talk about, which is that you need to be assured that Doit's going to accept your thing, which of course in a digital signature you can do because you yourself verified the signature. This is yet another protocol, but we can assure that as well. Okay.
Okay. So, I think you could now see that as students of Michael, we've learned